What's going on, everyone? Ali Reza here, back with a brand new episode of Iran Tech, and today I've come to Esfahan province at the heart of an industrial powerhouse of Iran, Mobarakeh Steel Company, which is not just the largest manufacturer of steel in the country, but the 10th biggest steel company in the world. But we're not going to be focusing on its size, we're going to be focusing on the precision and the science and technology that goes behind making various types of steel, each one designed for a very specific purpose. So think of a floating bridge, think of an oil pipeline, an earthquake resistance building, a skyscraper, and a car. The type of steel and the grade of steel used for each one is different. So today we're going to be exploring how you use different types of steel, how you add and remove different elements from molten iron to get the exact kind of steel with the exact kind of properties that you want. Stay tuned. Is the added or emission of carbon to iron, but just enough carbon. If there's too much of it, then the steel will become too stiff and brittle. If there's too little, it'll be too weak and malleable. So our job here is to find the exact right amount of not just carbon, but also other elements to steel. Steel is an alloy at the end of the day, an alloy being a combination of various elements, namely chromium, niobium, copper, etc., etc. And each one of these elements will add different properties to steel. So this is how we can get tens of different types and grades of steel at this factory, by adding and subtracting different amounts of elements and adding and subtracting the percentages of these elements to steel. But how do we actually precisely control that amount when we're dealing with something molten, so fiery and so unpredictable? Well, that's exactly what we're going to be finding out here. So let's go to the beginning.
Here, the steelmaking process relies on electric arc furnaces, EAF, which allows for greater energy efficiency and easier control over the raw material mix compared to traditional blast furnaces. It starts with sponge iron and scrap, melted at extreme temperatures. This is where the base of the steel is born. But here's where it gets interesting. In certain batches, ferroalloys like chromium, nickel, vanadium are added to tweak the microstructure. Take, for example, API X60, a corrosion-resistant steel often used in oil and gas pipelines. Its properties come from adjustments made right at this stage of alloying and composition control.
One of the capabilities that Fouad Mobarakeh has successfully achieved is the production of special API X65 sour service grades, which are used in sour oil and gas transmission pipelines. The key characteristics of this grade include high strength, good weldability, resistance to stress corrosion, and resistance to hydrogen-induced cracking. In our steelmaking process for this specific grade, we implement strict control over raw materials entering the production units. For example, we carefully manage the furnace charge mix in the electric arc furnace, add specific alloys, and reduce sulfur content to below 50 ppm, specialized operation carried out in our ladle furnaces. Additionally, we lower the hydrogen content in the steel to less than 1.5 ppm using advanced degassing units, which we have established at Fouad Mobarakeh. The casting process for this steel is highly specialized. Solidification must occur under controlled conditions to prevent internal slab defects. Chemical segregation in this product must be kept extremely low. One of the most fascinating challenges in steelmaking is balancing strength with flexibility. Let's say you want to build a structure that can stand through an earthquake. You don't want it to be so stiff it snaps or so soft it crumples. That's where seismic grade steel comes in.
To make seismic steel, the carbon content has to be pushed way down, less than 0.0002%. That's done using a unit called RH degassing. Think of it like a vacuum pump for molten metal, pulling out gases like carbon monoxide. What you get is a steel that bends with the Earth's motion, instead of breaking under it.
Once degassed, the molten steel is cast into slabs, but the job is not done yet. Impurities have to be minimized even further because even the tiniest bits can turn into weak spots later.
Now, depending on what the steel will be used for, those slabs go through different rolling processes, hot or cold. And that brings us to a special type of steel used in the automotive world.
One of the major concerns for automotive manufacturers is sourcing durable and lightweight vehicles. One of the best companies capable of fulfilling this need and the steel grades responsible for this task are advanced high-strength steels known as AHSS. Among these, dual-phase steels are the most prominent grades used in this category. Dual-phase steels, from a microscopic perspective, consist of two structures, hard and soft phases. The hard phase enhances strength, while the soft phase improves the formability of the steel.
And it doesn't stop at cars. From coastal towers to oil pipelines, different environments demand different steel behaviors, different steel properties, from anti-corrosiveness to pressure resistance and even surface healing. Each case demands the steel science to adapt.
Weathering steel, for example, forms its own protective skin over time. It's why some bridges age into that iconic bronze or green tint. It's not just beauty, it's chemistry doing the work.
At Foulad Mubarakeh, we typically align our strategies based on the needs of the people, aiming to contribute to their welfare. Given the current environmental challenges in the country, such as energy imbalance, water scarcity, and vehicle safety issues, we have naturally structured our product development strategies accordingly. Alongside environmental initiatives such as the water transfer project from the Persian Gulf to Foulad, we're investing in a 600 megawatt solar power plant for industrial use. Additionally, we're working on expanding our product portfolio. In product development, we focus on addressing energy imbalance, environmental concerns, and vehicle safety. We have worked on various types of steel, such as electrical steels, silicon steels, stainless steels, and high-strength automotive steels. Silicon steels, in particular, are a trending and advanced category globally, and we anticipate that most future vehicles will shift toward electric models, making silicon steels highly significant. Silicon steels come in two types, grain-oriented and non-grain-oriented. Grain-oriented grades are mainly used in transformers, while non-grain-oriented grades are used in motors and generators. Given that Foulad Mubarakeh is one of the most advanced steel production lines in the world, utilizing CSP, compact strip production technology, and capable of producing soft shapes, we can invest in alloy steels like silicon steels and stainless steels to master specialized grades. We must implement the technology triangle at every stage. This triangle consists of equipment, knowledge, and operator skills. At Sabah Steel, with expertise developed, we have worked on silicon steels. We have achieved production with up to 3% silicon content, making us one of the few countries in the world with this capability. By completing the supply chain, we can reach the highest grades of silicon steels. Due to their electrical efficiency and reduced thermal losses, silicon steels can significantly contribute to energy balance. Our calculations show that if water cooler motors in the country were replaced with silicon steel motors, we could save around 900 megawatts. a substantial figure. Silicon steels are also essential for electric vehicle motors, which are the future of the automotive industry. Currently, we have focused on non-grain-oriented silicon steels, reaching up to 80% silicon content. And we will later work on grain-oriented silicon steels as well. Stainless steel is one of the indicators of the country's development. A key development metric is the per capita consumption of stainless steel annually. Currently in our country, due to the lack of domestic production, carbon steel has been used as a substitute. For example, in parks and various public spaces, we see carbon steel being used, requiring annual repainting. If a stainless steel were used instead, there would be no need for repainting, and its durability, corrosion resistance, and life cycle would improve significantly. At Sabah Steel, we have produced ferritic and martensitic stainless steels and plan to work on austenitic and duplex stainless steels in the future. While we may acquire equipment for producing silicon and stainless steels, the knowledge is never transferred to us. We had to develop our own expertise domestically, leveraging internal resources, universities, and knowledge-based companies. We succeeded in this endeavor at Sabah Steel.
So the next time you see a skyscraper, a vehicle, or a power plant, just remember that behind every steel component, there's a calculated process of refining, shaping, and alloying. Not guesswork, but engineering. Steel might seem cold and hard itself, but making it requires agility, precision, and control at every step of the way. And that's exactly the kind of science that we feature right here on Iran Tech. And that's exactly where I'll leave it for today. I'll see you all next week.